Okay. So now we have, in this case, we will start from the end. Start from the end, what we mean that if we represent this alpha, so this is alpha 1, alpha 2, alpha n, and here we have beta 1, beta 2, beta n. Now we start the comparison from the end. In those cases, we started the comparison from the start, but from the reverse, we will start from the end. Okay, so here we have alpha n is equal to beta n, and if it goes on like alpha I plus 1 equal to beta I plus 1, and now here alpha I is greater than beta I. So we will check reverse. Okay? Now I will show you with an example. I will take a polynomial and I will check the comparison using all three orderings. Okay? G. White chalk, okay. So, here is my example. So we have f equal to, oh, what happened to my white chalk? F equal to 2x1 square x2 x3 plus 3x1 x2 cube minus 2x1 cube, and the ordering is lex. So now I have to check what is the leading monomial of this f with respect to lex. In lex, we have to check the value with the biggest degree. If we compare all three of these, the maximum power x1 lies where? Now I tell you what you people are doing. You are comparing the entire degree. My question was, what is the maximum degree of x1? Because in ordering, my x1 is greater than x2 is greater than x3. Right now, we are talking about only pure lex. Pure lex, it doesn't matter what is the degree of the entire monomial. What matter is what is the maximum degree of x1. So what is that? 3. So in this case, this is x1 cube. And what is the leading coefficient of f? Minus 2. Thank you. Now we consider deglex. Now we compare the degrees. Now you tell me what is the leading monomial of this polynomial. First one, which is x1 square x2 x3. Now we come to degree reverse Lexio order. So what is the leading monomial in this case? Now when we are comparing, we have to see the maximum degree of which? X3. So what we have? 1. 1?
Also first again, because there is no x3 in a second.
Have I written the question right? No, it's right. Yes. This is this one, which is x1 square, x2 and x3. Is it correct, sir? I doubt that. But never mind. Maybe I have written something wrong over here. It's okay. Okay. So is it clear now? Do you want to see another example or we should move on? We can do some things in the tutorial, okay? Okay. Now we have introduced the leading ideal. Now we will go directly to the definition of Grosvenor basis. Let I be an ideal in a polynomial ring x1, x2, xn, and let T be a monomial ordering. Then a sequence G1, G2, Gm of elements in I with lead of I is equal to leading monomial of G1, leading monomial of G2, leading monomial of Gm. Then this is called the Grosvenor basis of I. So the leading ideal of I is generated by leading terms of these monomials. So this is the definition of Grosvenor basis. Let us see a very fundamental result, which I am not sharing the proof of any theorem because they are books as told by Sir Pfister. One is a singular introduction to commutative algebra. The other one is Grosvenor basis, introduction to Grosvenor basis by Dr. Viviana N.A. and Sir Herzog. Is it correct? You don't know? Okay, so the theorem is Macaulay. Let be a monomial ordering on S and let I is contained in S an ideal. I don't have to write that, it's an ideal. Then the monomials in S which do not belong to lead of I forms a basis of S mod I, which give rise to another proposition, the famous Hilbert basis theorem, HBT. Let I in S and let G1, G2, Gm be a Grosvenor basis of I. G.
So what do you mean by basis of S quotient I? S quotient I is not an ideal. You mean the sub-algebra basis or something?
Sub-algebra basis, I think.
Yeah,
Okay. Grosvenor basis of I with respect to any monomial ordering. Then G1, G2, Gm is a system of generators of I. With the second, every ideal in the polynomial ring is finitely generated. So you all are familiar. Now we are moving to the process of finding the Grosvenor basis with the knowledge that what is our division algorithm. So you all are familiar with the division algorithm for a single variable. What is that? If you can remind me. What is the division algorithm for polynomial of polynomial ring of single variable? Absolutely right. So now the idea is the division algorithm. Now what we have is that if we have a polynomial f in a polynomial ring S, there exists G1, G2, Gn such that we can find Q1, Q2, Qn, that f is the linear combination plus R, where this R is the remainder. But in the case of polynomial with multiple unknowns, it doesn't end here. Now it has additional two conditions. The one condition is that no element of support of R is contained in the ideal L leading monomial of G1, leading monomial of G2, leading monomial of Gn. This is the first condition. The second condition is like leading monomial of f is greater than equal to leading monomial of Qi and Gi, where I is greater than equal to 1. Now we see an example. We will take a polynomial f and we will take another polynomial and apply this algorithm on that. So we have f equal to x1, x2 plus x2 square, and we have g1 equal to x1 plus x2. And the ordering is lex in our case. Now we have to see, can we write f in terms of g1? How? F equal to x2 g1. What is the remainder with respect to lex? Is there any remainder? No. The remainder is 0 in this case. But if we change the ordering, if we take g2, my g2 is missing. If we have g2 equal to x1 only, then, and the ordering is same, we can write it x2 xg1 plus x2 square. So here our remainder is x2 square. This is our remainder. So yet we haven't reached to the point of using this to find the Grosvenor basis. The Grosvenor basis says that firstly the remainder needs to be 0. So whenever we are applying f, so we apply f g1 on f and we get remainder 0. Here we apply G1 and we get the remainder x2 square. De Waal algorithm says that if we get a remainder which is not 0, we add this in our Grobner basis. This is the process. Okay? Now we will write the formal definition of how to summarize all this what we did on the board.
So the process continues till we
Yes, till we get the remainder as 0. So the process leads up to the S polynomial, which will provide us to the definition and lead us to the ideal membership. So if you want to see another example, we can do that in the next session. So let us write the theorem where we lead to, which is let I in a polynomial ring S be an ideal and G equal to G1, G2, Gn is in, let it be M, is in I. Then the following are equivalent. I'm a bit lazy, so that's why I'm writing FAE, following are equivalent. So the first one is G is the Grobner basis of I. Second is F belongs to I if and only if F approaches to 0 with respect to this Grobner basis. Okay? But the process, what is the process? Process is using these GIs to reaching to the point 0. So it's not like that we have reached to this point in one attempt. No. It might be multiple. Okay? So if I have time, in the end I can do a question and show you how I reached to this point. Okay? So for this example, it's clear how to get to this point. Okay, so now we have the famous, I don't know the German pronunciation, but Buchburger. It's not that burger we used to eat, but it's Buchburger. So this is one process, and this gives rise to another process. Okay, so I will write you the way I did before, that I write the process, and then we will move through the theorem, which is the Buchburger algorithm. So firstly, I will let you know what we are doing. So we define a polynomial which is a S polynomial. And if we have a set G, and it has G1, G2, Gm, what this S polynomial do is that we calculate for each G1, G2, let it be Gi and Gj, for all I not equal to j and I from 1 to m, we calculate this polynomial. This polynomial is designed in a way that it cancels the leading monomial of each one of these, and then check whether the S polynomial is reaching to the 0 or not. What we mean is that we want to see that it approaches to 0, then it means that there is nothing added to this Grobner basis. So for that reason, we have to check for each one of these. But one very important result which helps us in, you can simplify the process, is that whatever the ordering is, if two polynomials are relatively prime, if they are relatively prime, then the S polynomial of f and g is 0. So if you have more than like 5 or 6 or 10, checking for all such pair is very difficult. Okay? If you have m elements, then you have to choose 2. So there are a lot of elements. So for that reason, you have Macaulay and singular to help you simplify the stuff. Let me now define the S polynomial. What is an S polynomial? So the S polynomial is missing. So we have S F G equal to LCM of leading monomial of F and leading monomial of G divided by C into leading monomial of F into F minus LCM of leading monomial of F, leading monomial of G, divided by D, leading monomial of G into G. Now my question is, what are we doing by adding this here? What are we doing? So C is the leading coefficient of F and D is the leading coefficient of G. So we are actually getting rid of the leading monomials from here and we are getting the rest of the part, which is, you can say, a tail. So what is a tail? So if I have a polynomial x1 square, x3, x2 plus x4. So this is the leading monomial and this is the tail. Something which is not a leading monomial and the rest part is known as tail. So if you read any commutative algebra book and it's written tail, it means that it's something which is not the part of the leading monomial. Okay? So this is the S polynomial. So for your convenience, what we will do is that we will do a question because it's important to show you an example where you can use this polynomial and why we need this. Okay, so we have I equal to G1 and G2. My G1 is x, y minus z square and G2 is y square minus xz. Okay, and I'm using simple lex, and by lex we have leading monomial of G1 is xy and leading monomial of G2 is xz. Now we will add this in this formula. In S, G1 and G2. When you do the calculation, I will just, because I'm a bit lazy, so I will write minus z square. This is y square minus xz. And when we cancel, we get y cube minus z cube. We get y cube minus z cube. So, what is the remainder? What is the remainder? Does it finishes here or it moves somewhere else? My papers are all messed up. Okay. So, can we simplify it? By G2 only? So if this is reaching to 0, it means that I equal to G1, G2 is the Grobner basis. If not, then we add this and call it a G3, and then we do calculate the S polynomial again using SG1, G3 and SG2, G3. And then if these both gives you G, 0, it means that this is the Grobner basis. If not, then we add that one again over here. So we keep on doing this process. Yes?
What is the guarantee that this process will always goes to 0?
Because the polynomial ring process is Noetherian. Noetherian is that all such chain terminates.
That's I think about the ideals.
Ideals, yes, it is. The chain is of ideals. What is that? It is that I1 is contained in I2, is contained, it goes on IK, and it says that there exists a J such that IK is equal to IJ. Okay. First, I need to fix my papers, if you give me 1 minute. Okay. Okay, so this is the theorem where we are heading. This theorem states Berger criteria. It states let be a monomial ordering on S and I equal to G1, G2, Gm, be an ideal in S with Gi not equal to 0 for all I, then following are equivalent. मज़े की बात है, उर्दू में बताऊंगी कि अगर मेरी क्लास होती और उसमें कोई बोल रहा होता ना, सीरियसली मैंने बाहर निकाल देना था. मैं झूठ नहीं बोल रही. Thank you. Did you understand what I said? Okay. So G1, G2, Gm is a Grobner basis of I with respect to any monomial ordering. Number 2 is if S, Gi, Gj reduces to 0 with respect to G1, G2, Gm. So this is the famous Buchberger algorithm which states that you have the polynomial Grobner basis if all such combination of S polynomials approaches to 0. When we say approaches to 0, it doesn't mean that we are doing some continuity. No, it means that we can find linear combinations that you reach this thing to 0. Okay? Okay, now I will show you the process. So I have f equal to x1, x2 minus x3, x4, and g is minus x2 square plus x2, x1 and x3. Now we will calculate the S polynomial. Help me. So you all have the formula. So we have how much time? 17. 10. He's giving me seven more. Okay. Now what I want you people is that do it yourself. I can wait till I can make you pain for a bit to show you the tutorial that how easy it is by putting it in a computer. So what is SFG? X2F plus X1G. So what is the remaining part? What it is doing, let me do it for you. Minus X2, X3, X4 plus, which is actually minus in our case, X2 square plus X1 square, X3. Is it correct? So now you are able to cancel the leading ones. Now you have X2, X3, X4 plus X1 square, X3. So we are considering reverse legs. So degree reverse legs, okay? Now the remainder is not 0. So what we will do? Yes, we add this here and I call it H. Now what do you have to do? Yes, now you have SFH and SGH. Because I'm not that evil, so the remainder is 0 in both cases. Okay, so now I equal to FGH is the Grosvenor basis. This is one application of looking at it. And I tell you, as a student myself, because I am, that this method is the heart for finding the Grosvenor basis. And it's very helpful when you are like studying yourself. It's going to be helpful. You can tell your friends that I know that, so it's going to be easier for me. If you need the notes, so do we have any WhatsApp group so that we can send the notes on that WhatsApp group?
You can send those notes to us and we will share them with the participants.
Okay. So let us move to another application, which is elimination order. Any question? सवाल पूछ सकते हैं, बोलने से डंटा था. Okay, so let us move to the elimination order. So first of all, I will define the elimination order. And write an theorem related to it, and then I will show you by an example as I did, so that the concept is more clear. Okay? So the elimination ideal is, let I be an ideal we all know now, and T is between 1 and n. The ideal I, T is I intersection with k x t plus 1 till xn is called an elimination ideal. It's better to write the theorem first and then show you an example. Okay, so the elimination theorem states, let, again the same roll up, is ideal and T is between 1 and n if G is the Grosvenor basis of I with respect to any ordering elimination, respect to elimination ordering. For x1 is x1, x2, x3, then gt, g intersection with k, xt plus 1, xn is the Grobner basis of the elimination ideal. Denoted by IT. Let us see an example. I equal to x1 square, x2, x3, x1, x2 square plus x3 cube, and we have x2, x3 plus x3 square contained in k, x1, x2, x3. And the Grobner basis with respect to lex is all these union with x1, x3, x2, x3 and x3 raised to power 4. Now, in order to find the t, let it in our case be 1, then it is I intersection with k, x2, x3. If it says find the elimination ordering of 2, it means I intersection with 2 hai. If it's 2, it's starting with plus 1. So in our case is x3. So what do you see? Wherever in I you have x1, you eliminate that part. So in this case, what is eliminated? This one is eliminated, this one is eliminated, and we are left with x3, x2, x3 plus x3 square and x3 raised to power 4. So this is our elimination ideal. And when we are finding elimination order 2, then this is in our case x3 raised to power 4. So whichever t we are eliminating, we check the intersection and we eliminate it from the Grobner basis. Okay? So now what you get is what? What is this? This is the Grobner basis of the elimination idea. So now I need to give you the references for the books. So the first book is A Singular Introduction to Commutative Algebra. By Grohl and Pfister. Second is Introduction to Grobner basis by Viviana Annie and I don't know the spelling, but Herzog. And this is more important when you don't have that much time to do everything by your hand. So there is all the notations and the end of the book, all the formulas or the parts you can use. Any questions? Thank you very much. Yes.
We have to start another session, online session. Could you please join it? Please start the online session.
Thank you very much.